All right. So thanks, Konstantinos, for the introduction. So today I'm really excited to share my recent work on building multimodal clinical foundation models with domain-aware DRPO training. And first, I'd like to start with some background and on why we want to build clinical analysis AI models. So in the past years, there has been more and more multimodal data available publicly, and there has been like an increasing demand to make quick initial diagnosis, especially in the emergency department. For example, like in the emergency department, doctors are often presented with a patient, possibly with a very long health record and many data, where doctors are not able to reveal all this data. Another example is in the underserved and developing countries. For example, like my hometown, doctors usually only had maybe around like 2 minutes to look at everything and write up the diagnosis. Within such short period of time, it's easy to omit relevant information that may be useful. And this is where machine learning comes into play. If modern like large language models are able to make a quick initial diagnosis with reasoning highlighting possible evidence from a large pile of multimodal patient health record, it'll be super useful to assist doctors making a quick diagnosis in a very time-constrained environment. And there has been many attempts in developing like multimodal diagnosis models. Traditional classifier models can only diagnose diseases that they have been trained on, which requires extensive training data for each disease category. So it's usually constrained to a small subset of the diseases. And more recently, thanks to the extensive clinical text the large language models are pre-trained on, it can produce really decent outputs. But we found that it often struggles with a multimodal medical data, which is typically not available freely online. And also, none of the current models accepts raw time series as inputs. And even though the current reasoning multimodal large language models are not performing that well, we still believe it's the future of like AI-assisted models, mainly because of two reasons. So first, simple encoder-decoder-based models is usually not super interpretable, even though you can add something like perturbation-based interpretability method to it. Practitioners usually find it hard to use without explicit text stating like the model's own logic. And also, reasoning multimodal large language models provides a way to verify models' logic with human-readable text. And the second thing is that some complex problems, like the one below here, requires multi-step reasoning. For example, here the model needs to gather information from like multiple sources and consider the interactions between them in order to arrive at a single like final answer. So this is very challenging for most of the traditional models. So to address these problems, there are many challenges we need to solve, but the aim of this project in particular is to develop a multimodal large language model that can reason across multiple modalities. So we aim to address this problem in this project. We start by designing the model architecture and then move to the training algorithm design, which is the main focus of this work. So the modeling part here is actually pretty simple. We have a time series encoder to encode time series data, a single vision encoder to encode all like 2D, 3D images and video data. And we have text tokenizer, which comes with a large language model backbone. So these encoders are followed by a projector, which projects it to the large language model token space. And finally, they are all like concatenated together as a single sequence for large language model to digest. We train the model so that it can output reasoning insights, city and region annotations before making a diagnosis. guess I'd like to maybe pause here a bit to see if there's any questions that anyone want to ask. Guess if not, I can continue. Okay.
Maybe I can have one quick one. A lot of people in our group work with different time series data, biomedical time series mostly. So EEG, ECG. I can see Fu has a question as well, who's working on ECG. Did you consider any specific time series encoder for each of these, or was it one encoder for all of them?
Yeah, for this work though, we are only focusing on the ECG data from the time series modality. We plan to expand that to a more general time series embedding model, which I think will be more powerful and more useful in more scenarios. But for this work, we just use the ECG encoder, which is called ECG JPA.
Fu, do you want to unmute and ask?
So hello, David. So I have a question for you. So now I also develop a multi-model learning for ECG and test, but I am wondering, so does your model learn a strong representation or only focus on a task-specific reasoning pipeline? For example, does your model learn a sham embedding space or fuse modalities inside to the large language model? So So, so for example,
Yes.
if we instruct ECG encoder in your framework, and is it good for a specific task, a specific disease?
Yeah. For the ECG encoder, we train it on a bunch of different ECG diagnosis datasets. So I guess the capability uh of the encoder itself is limited by the dataset we train it on. So yeah, I don't have a specific list of the datasets here, but if you check the original paper, you can see what kind of conditions can you understand based on the training data.
Yeah, thank you. Thank you so much.
Okay, yes, I can move to the next slide. Also, to better elicit model's reasoning capability, we wish to train the model with reinforcement learning. So we designed three very simple rewards. The first one is the accuracy reward. Since we have the ground truth label from our multimodal data set, we assign a reward of 1 if the model's final answer is correct and 0 otherwise. And secondly, we ask the model to include a bounding box, highlighting the salient region it uses to arrive at the diagnosis. And then we measure whether the region is consistent with the ground truth region and assign rewards based on the IOU score. And lastly, we want to encourage the model to make sufficiently long reasoning, but not too long. So we design the last length reward to give a reward of up to 1 if the model's reasoning is at least 100 tokens, but no more reward if it's longer than that. Also, to train a model of this scale for universal diagnosis, we also need a large dataset. As a preparation for this project, we collected one of the largest public clinical datasets, which is called CLIMB. So CLIMB is mainly a clinical diagnosis dataset, and you can see from the input plot, you can see the input spans from ultrasound videos to graph representing brain MRIs, as well as time series data representing EEG and ECGs. Although for this work, we are only using ECG, we don't have a EEG encoder for this. And you can see here is one of the largest public data sets for clinical diagnosis, both in terms of number of QA pairs as well as size. We have a total of around like 4 million samples and a total size of 19 terabytes. And if you are interested in using this data set as well, feel free to check out the paper linked in the archive here. Also made a public code repo so that you can download many data sets and process them in one click. So you can train large language models with all this data with one script. Feel free to scan the QR code here to take a look. And we're also working to add more data sets, and we would really appreciate community contribution on adding support for more data sets if possible. And so the architecture and reward design is pretty simple. We have a pretty good like multimodal data set which we can utilize. But the bigger question here is how can we train this model so that it can work on this highly heterogeneous data that we have? An easy approach is to follow the recipe of DeepSeek R1 paper and use their post-training method, which is DRPO, or other variants of DRPO like DAPO or something else. We tried training with DRPO reinforcement learning, but we soon found a critical issue. So the issue is that DRPO treats each of the input sample equally and normalize across like all rollouts of each sample. So each individual sample has like roughly equal contribution to the gradient of each step. And as a result, the model tends to focus too much on the easy and abundant domain, while just completely ignore the hard and also scarce domain. You can see here, if we train the model with our climate data set, we see the model exhibit like improved performance on easy and abundant domains like trajectory, but no improvements on hard and scarce domains like ultrasound. And after some investigation, we see that the issue is likely related to the high heterogeneity of the input multimodal data. And we see that DeepSeek R1 is actually a text-only model with input data being like relatively homogeneous. So DRPL works pretty well. But for the highly heterogeneous data from time, we have data across like vision, time series, and text, all of which varies a lot in terms of distribution, scarcity, and difficulty. And this is why we see performance varies this much in our initial explorations. And to solve this problem, we proposed another reinforcement learning algorithm, which is called domain-aware DRPO, or we call it like DRPO. So the idea here is pretty simple. We want the model to focus more on harder problems. To achieve this, we develop a hierarchical clustering scheme. We first cluster samples with its inherent domain. So for example, the X-ray images fall into one big cluster, and the ultrasound will fall into another smaller cluster. And then at a more fine-grained level, we employ k-means clustering based on the downstream reward patterns, such that harder samples within each domain will fall into one cluster, and easier sample will fall into another cluster. So the exact number of clusters at this stage is automatically determined by the elbow method from the k-means. And finally, we assign a scaling factor for each cluster and scale the reward based on the two-stage clustering scheme. So this way, we essentially upscale the rewards on scarce and hard questions and downscale on the easy and abundant questions. And this way, we let the model focus more on harder questions in the data set. So kind of I quickly skip over the algorithm a bit. So I'd like to pause here to see if anyone has any questions regarding the algorithm or like the training setup.
Maybe I can start with that. One quick question. Do you think so the question is, why did you need the clustering in the first place and not just decide based on the reward that its sample got? Why did you need to cluster them together?
Yeah, I think the idea behind the clustering that we want to form a pattern. We want to study from the pattern that the model gets based on the reward patterns. So the model spans from like different modalities. So that's like one way to cluster the question together and to optimize it collectively. The other way is that like within each clinical domains, we also see that the model exhibits some kind of like clustering. So some of the rewards they have a pretty like low reward throughout the learning process, and some have like a high reward sometimes and low reward other times. So the clustering is not based on the mean reward itself. It's based on the reward patterns. So from the RL training, we have like multiple rollouts for each of the samples, which means that the model outputs like multiple answers for each of the given input question. And we use the patterns, not the like the mean reward for each of the samples, so that for example, like the samples that have high reward and a low reward will fall into like one single cluster, which will be optimized collectively together. And the model to have a consistently like mean reward, for example, of like 0.5 throughout all times, will get into cluster into one other cluster.
Okay. Was it important that they are clustered together, like that these points that they have, let's say, somewhat of a similar reward, mean reward, were grouped together? Or did you see that in those clusters you had specifically like some tasks or some modalities? I mean, conceptually, what was these clusters at the end?
Yeah, I guess I kind of skip over a few details. So, besides the mean reward cluster scaling, we also have the number of like questions in the scale. So yeah, I'm trying to not get too much into details, but sometimes we see that if the model has if a sample has a reward of like always 0.5 throughout all rollouts, the model is actually essentially not learning anything, because like after normalization from DRPO, all of the rewards from this particular sample will be normalized to a mean of 0. Like the model will actually not learn anything from this sample. And this scenario or this kind of patterns, we see this kind of patterns more often as we move towards later stage of training, where the performance kind of saturates. But the more valuable sample is something that, for example, have a very low reward sometimes, but have a very high reward other times. During the learning of these kind of samples, the model will learn to move away from the low reward sample, low reward rollouts, and more closer together to the higher reward rollouts. And these are more valuable samples, which will get smaller and smaller to the later stage of training. So besides the mean reward, we also have a frequency reward, where we actually upsample the samples from clusters that are smaller. So essentially, in the later stage of the training, the samples with high variance in reward will get upscaled as well. So that's another stage of upscaling where which allows the model to focus more on the higher valuable samples.
Okay, thanks. Maybe Stay, do you want to?
Yes, hello. So I wanted to ask a question about the design of the reward. So you defined this semantic alignment reward. I think it was on 8 or 7, yes. And I wanted to ask, is there an analog for ECG? Because, for example, in this alignment reward, it seems to focus on the images. But in that case, does this mean that the interpretability reward is focusing on some of the modalities? And would that bias the training to focus towards imaging-based solutions, let's say?
Yeah, I guess the question is on whether this focus mainly on the image and not like other modalities like videos or time series. Is that right? Okay. Yeah. Yes. We have well, I think the semantic alignment reward, this is mainly for the vision. So we don't have that for time series. But for videos, we can assign like ground truth bounding boxes for each of the frame in the video and also the 3D images. So the way we process the 3D images and videos currently is to convert them into slices. So for 3D images, we slice them equally, uniformly into like multiple parts. For videos, we slice the frames with the equal space. And each of these can be assigned a semantic alignment reward for each of the bounding box.
Okay, thank you. But there is no reward for explanations based on, let's say, parts of the ECG.
You mean the time series or?
The time series, yes, the ECG time series.
Right. For this work, we don't have the alignment reward for time series yet.
Okay.
I mean, it's technically possible to assign the reward if you have some way to represent like a part of the time series. And it will actually be very useful. But the thing is, I think the issue here is that we don't have the supervision on that. For images, a lot of the data sets have the ground truth like ground truth bounding boxes on the important regions. And for those that don't have, we have automatic ways to generate these supervisions. But for time series, I don't think we have that reliable way to supervise like which of the exact region is most important.
Okay, thank you.
Thank you. Okay, guess I can move forward. And with this method, we train the multimodal large language model of up to 32 billion parameters on 8 H200 GPUs. We see that DRPO, which is our method, outperforms much better than the vanilla DRPO on our dataset, especially on understudied modalities like ultrasound and CT scans. And you can see here in the figure, the model's performance on ultrasound and CT scans are much better than the model trained with vanilla DRPO. We also see that the 32 billion parameter variant performs much better than closed source commercial models like GPT-4o and O4 Mini, as well as the open source specialized models like MED-R1 and LavaMed. And we also see that DRPO algorithm perform better than the all critic-free RL baselines. as well as SFT and PPO. And on the efficiency side, we also see that the algorithm has pretty minimal overhead. On AH100 GPUs, the entire reward calculation takes only less than 10 seconds, whereas the entire step takes more than like 400 seconds. So our algorithm only adds less than 1% of the time, which is pretty minimal considering the entire training duration. And because we train the model with reasoning, we also collaborated with medical professionals to annotate the relevance of the model's reasoning traces. Out of the randomly selected validation samples, we see around 45% of the reasoning traces are highly relevant to the final diagnosis, and all of the annotated samples contain highly relevant reasoning traces. And here is an example of the reasoning trace. You can see the model is able to correctly identify the bad parts in the image and refer to its own medical knowledge to explain why it thinks this is abnormal. And then it arrives at the final diagnosis after all this explanation, which is correct. Here's another example where the model reasons across X-ray images to make a correct prediction that the patient will only stay in the hospital for less than 4 days. And here's another similar example. You can see that the model can not only refer to the issues in the ECG and X-ray, but also refer to the electronic health record as well, to conclude that the patient will likely stay in the hospital for a longer period of time. And of course, the model isn't always right. We also did error analysis of when the model is wrong. Sometimes the model is not able to identify the correct feature. This happens often in harder modalities like ultrasound. And in this example, though, the model actually finds the correct feature, but somehow arrives at an incorrect answer in the end. And I guess in the future, we hope to further developments in the multimodal large models and clinical diagnosis can help mitigate or solve these kind of issues. And besides the model and dataset contribution, we are also developing a code repo that focuses on RL training on more modalities, including audio, time series, and more. And the code repo here is based on Vero. So if you are using it already, the basic architectures should be sufficiently similar. We also welcome community feedback on this, so feel free to open pull requests or report bugs with the issues if you want. And I guess lastly, I'd like to thank my collaborators, Peggy, Chanakia, and my advisor Paul. And the project won't be possible without them. And I guess that's the last slide of the presentation. I'd like to take any questions if anyone have any.
Thank you very much, David. Very interesting presentation. Let's see if someone has any questions. Yeah, please go on and you.
Hello, thank you for the presentation. I was wondering, so this was mainly for fine-tuning these models, right? The reinforcement learning and the reward strategy. But your original models, how are they pre-trained? Did you use a pre-trained model from literature, or like what was your pre-training strategy for the encoders of the time series and the 2D divisions and the text?
Yeah, great question. So here, for the training of our model, we started with the pre-trained model, which is a Qwen 2.5 VL at the time. We also later we updated the model to use a Qwen 3 VL backbone instead. So this is run like 8 billion to 32 billion models. So we actually had two variants. One is the 8 billion parameters, and the other one is the 32 billion parameter as a large language model backbone. So that's why I don't have like the exact parameter count here. And the vision encoder, this comes with a large language model backbone. So this vision encoder is also from the Qwen 2.5 VL. So we don't have to align this. The time series encoder, this one is also pre-trained. We use a model called ECG JAPA. But the protection layer here is like randomly initialized at the start stage of training. So we do need to align the time series encoder with the large language model backbone.
Okay. Thank you.
Yeah, thanks for the question. Okay, any other questions?
Please, Fu, go ahead.
So I have a question. So I want to confirm whether your framework is a combination of image, time series, and test modalities trained together, or if you train image test or time series test separately.
You mean the text modality, right?
Yeah, yes. Okay, you combine
So-
on image test and time series, and you train all of them together, or you train the pair of image test and or the time series and test pair separately.
Right. Yeah, actually, most of the training data only has a subset of these modalities. So because we concatenate all of these tokens together, the model can accept any combination of the input. So you can input only time series and text, only vision and text, or even only like text alone. So these are all possible with as an input.
Okay. Thank you.
If I can ask another question. So I see in your model here, you use a time series encoder for the ECG and a vision encoder. Like these embeddings, are they concatenated or averaged?
Yes, the embeddings here are concatenated together. So the nice thing about the large language model backbone is that it accepts a variable length of inputs. So you can have any length of input, and you can understand and reason about it, no matter like how long the inputs are.
And do you then give a sort of positional embedding, like an embedding, like to say to the vision encoder which kind of modality is present? Like, do I have an X-ray or do I have a CT scan or an MRI?
Yeah, that's a great question. So we have like for the vision encoder is handled by the large language model itself. So it has 2D positional embeddings, and it also has special image tokens, which represents the absolute position of each patch in the patchified image representation within the input. So essentially, the positional embeddings it assigns like the 2D position in the 1D sequence. And for the time series, we kind of mimic the how the model handles the images. So time series, even though it's multi-channel, the time series encoder it combines multi-channel ECG into like one single token for each of the around like 5-second chunk of the ECG input. So the way we handle this is that we add a 1D positional encoding for the time series. So it's not 2D as in images, but it still has the positional encodings. and also add special time series tokens to note the start and the end of time series.
Okay, thank you.
Thanks for the question.
Maybe if I can ask a closing question. We've been discussing from time to time whether these traces, these reasoning traces, should be supervised in any way, and whether that could help the model. So based on your intuition and the experience that you have gathered with all this effort, do you think it's a good idea to supervise the learning traces? Could that be a reward? Would that be feasible to gather such supervision in the first place?
Yeah, I feel like supervision on the reasoning is certainly very useful. There are some very recent works. So there's kind of like a shift in the focus from the research community. So from before the DeepSeek R1, people like process reward. They like to supervise on the reasoning traces. But the DeepSeek R1 paper actually mentioned that process reward is easily like hackable, and we shouldn't add any kind of process reward. We just need to add the final answer reward. So this work can kind of follow that patterns. We have the reasoning. We ask the model to output reasoning, but we don't actually have a supervision on that yet. And after this work, like in the past few months, there has been a few more works that actually thinks, well, process reward when acting correctly may be beneficial. I can share papers of that topic afterwards, but essentially they are trying to add a few more like other rewards that supervise on the reasoning. But I think right now the more popular approach is to use distillation. So either like self-distillation or like distillation from a more stronger teacher. So I think one approach is that first you train the model and you tune the model with RL so that it outputs some kind of reasoning traces, and you save the reasoning trace and you do a later stage of like SFT tuning on the correct reasoning traces. So the definition of correctness depending on your domain of trainings. But I guess one easy thing you can do is that if the model's final answer is correct, you assume that the reasoning is correct, and you do SFT on the reasoning traces, and after SFT you do another stage of RL on the SFT tuned model, and people show that this actually have the best results with compared to only RL. But I guess
Thanks,
the
that's
most
very
important
interesting.
thing here is that if you want to do reasoning trace on like time series, you essentially don't have a stronger model to have to help you with like self-distillation or something. So that will be a bit harder.
Okay, thanks. Very interesting, and I would be glad to distribute later the papers you're mentioning. Fu, please go ahead.
Yes. David, you are concatenating tokens from different modalities and fitting them into the large language model for fine-tuning. So have you evaluate into how much modality actually affects the overall performance? So I mean, for example, what happens if you drop the image encoder or you drop the ECG encoder? How much does the performance change?
Yes, we actually have some experiments on this, which is not on this slide yet. Let me see if I have that over here. So here we have the rewards on the mimic dataset, and we have some applications on the modalities. So you can see here, so this is on the mimic 4 dataset on doing two kind of standardized tasks. One is length of stay, and the other is 48-hour in-hospital mortality. So you can see here, the model trained with full combination of modalities, which include time series, vision, text. It achieves the best performance. And the second place is the vision plus text. So this is no time series, and then it's ECG plus text. So the text-only modality achieves the worst performance among all the ablation of the modalities here. But you can also see that the vision is actually a stronger modality than the time series. So removing vision has a stronger detrimental effect on the final performance as compared to the time series. So I guess future improvements, future developments can focus more on like how can we get a better time series encoder, how can we better align the time series part to the model, because apparently like the vision here is still a stronger modality.
Thank you so much.
Okay, so just we wrap up here because I know David has to go at 12 somewhere. Thank you very much for joining us, for presenting. I think it has been quite interesting, and I hope people enjoyed it.
Yes, thanks also for the invitation.
I can see some hands, but I assume they are coming and going, so I don't know. Okay. It was clapping. Thank you very much, David. Have a good day.
Okay, thank you so much.
Thank you.
Nice, really nice meeting you guys. Thank you.
Thank you very much.
Thank you.